Okay. And, oh, I'm switching all sorts of, I did not want gallery view on. My views changed from what they normally are. If you can't see, like if suddenly I'm talking and what I'm talking about is not on your screen, please tell me because my screen may not look like the same window that you guys have. So either interrupt in the chat box because that'll pop up in front of me, or just take yourself off mute and let me know, and I will make whatever adjustments you need because it's looking different to me than it normally does. But I just kind of changed up some of my um, tech that I was having issues with, and so I want to make sure it's set up correctly. Okay, so the first thing goes back to that chapter where we were doing some of the quality. And so I actually am going to have you do one of the graphs. I don't know if you can remember, it feels like a lifetime ago, but all the way back when we did our lab in class where you had to draw a bunch of graphs and plotted a bunch of points, and some of you were a little more vocal in your displeasure about having to go through that process. But to show you that it was not a waste of your time, you're going to do that process on the exam. So if you have your notes from that lab, those notes would also be helpful to you for the exam. And you should have those. Those didn't get turned into me, you kept them. So if you still have those notes from earlier, I would definitely pull those out when you attempt the exam. So the first thing is just looking at the process capability. And the process capability is a very easy formula that is equal to the mean value that you're given plus or minus 3 times the standard deviation. And so you need to just look for the two pieces of information that you're given, the mean and the standard deviation. And we talked about it in class that the reason that this is true is because when data is normally distributed, you have your nice little bell curve and the mean is in the center, and then plus or minus 3 standard deviations from the mean is 99% of all of your data points. And so that's why the process capability is equal to the mean plus or minus 3 standard deviations. So in this case, it's equal to 32.021 plus 0.033 and 32.021 minus 0.033. And those are both multiplied by 3. Those 0.033s are then multiplied by 3. It's a whole bunch of 3s. So in this case, you have a range that goes from 32.120 to 31 is the low end, 0.922. And so the math is super simple. It's just this one formula here for process capability. And the problem itself should give you, just like this one did in the writing, it should give you the mean and the standard deviation. So you just plug those values in. But when you're asked for the process capability, you're not giving one answer, you're giving two. It's both of these are the answer. So when you see this on the exam, don't just solve for the mean plus 3 times the standard deviation. Make sure you do both the upper and the lower value, okay? And that's because if you were looking at this on the graph, your mean would be in the center, your upper value is at this end, your lower value is at that end, and that's how it would normally be presented. You don't need to draw the graph on the exam. All you need to do is complete the calculations. All right, the next one. Now, hopefully you have the document in front of you because I'm not going to review all of this. But this goes through what you have for your, oh, and this actually has typos. I uploaded the correct one for you, but this one actually has typos, so I'll rewrite those. So what they're telling you is that you have 5 parts taken each time you do a sample. those 5 parts, then they calculated a average, your X bar, and your range. So if you remember your average, Andrew, yes, it's being recorded, and I'll post it to Blackboard later today, but it is being recorded. Thanks for the question. So the average was adding all of those up together and dividing by the number. And then the range is the highest minus the lowest. Now we did that in that lab, and that's why I was saying if you still have your notes from the lab, you should pull those out. But we did that in that lab, and you had to calculate all of those on the table, and then we drew the graph. In this case, it's already been calculated what each of those individual samples were. And that's the same way it's going to be on the exam. You're not getting a bunch of raw data. You're going to be given data where they've already calculated the average and the range for each individual sample, which means to draw your graphs, the only thing you need is the average of the averages and the average of the range. So the average of the averages is called X bar bar. And X bar bar is the average of all of your X bars. So I'm going to add all of those up and divide by 7. And in this case, my X bar bar is equal to 1. My R bar is equal to the average of the ranges. So that means that I added all the ranges up and divided by 7. And in this case, your R bar is 0.0133. These are the center lines for your graphs. Your X bar bar and your R bar are your center lines. So I did this on graph paper. I am not doing it on graph paper now. But if you freehand it, I understand that your freehand may be just about as good as mine. If you put it on graph paper and have it neater, that lets me give you more points because I can read it more easily, but it's kind of up to you. If you feel that you can freehand it and give it all the detail that it needs, that's great, go for it. If you are a little sloppy in your handwriting and you're worried about me not being able to read your writing or something, I would just use graph paper and upload that page separately. So starting with your X bar chart. So we're going to do X bar chart first. And the X bar chart, you're going to be given an upper control limit of X bar and a lower control limit of X bar. And the upper control limit, that's where the typo is 1.0077. And your lower control limit is 0.9923. That information is given to you in the problem, and it will be on the exam as well. Then the other thing you need to know is your center line, which is X bar bar, and that's 1. So when I draw this, and I'm going to kind of freehand abbreviate here, I have my x-axis and my y-axis. So along the bottom are my samples, and I have 7 of those. So 1, 2, 3, 4, 5, 6, 7. That's my samples. And I'm going to plot for every sample the actual X bar that was calculated. And that's given up in this table, those X bars. These are the points that I'm plotting. These 1 through 7 right here. That's what's going to go on this chart when I start plotting. Now on the y-axis, I have my lower control limit, which is 0.9923. That was given to me. And your lower control limit is a solid dark line. And you write at the end of it, LCL. I have my upper control limit, which is 1.0077. I know I wrote that super tiny, but you also know what it is because it's written up here. And I draw a solid line for that as well, and that's my upper control limit. Then I need to add my center line. My center line is approximately in the middle, and that's just at 1. The center line is a dash line. And I call that dash line X bar bar. So to draw this chart correctly, you need to have a solid line going across the top at the upper control limit, a dashed line that says X bar bar going at the center line that you'll calculate, and a solid line going across the bottom that's the lower control limit, and that also is given to you. So you're given 2 of these, you calculate this one, and then you plot the data. So in this case, sample 1 is above the line, then sample 2 is kind of right below, sample 3 drops a long way, sample 4 goes back up here, sample 5 is back down around this one, 6 starts going up again, and then 7 is up here towards the top. And so I can plot these and draw the chart like that. That is your X bar chart. Your R bar chart is the exact same thing using the R values. So for your R bar chart, you've got your upper control limit of R bar, which is given to you, and that is equal to 0.0281. And you've got your lower control limit, which is given to you as 0. And then you calculated your R bar, and that was equal to 0.0133. And so again, I'm going to draw my X and Y axis. My X axis is again the 7 points, 1, 2, 3, 4, 5, 6, 7, and I label that as R. And then my y-axis here, the lower control limit is actually 0. So I'm going to write down here, lower control limit. My midpoint, my R bar, is 0.0133. And then my upper control limit was 0.0281. So I'm going to put another solid line for my upper control limit. And then I'm going to put a dashed line for my range, my R bar. And so again, when you hand this in, you should have your x-axis with the number of samples going across, your y-axis with your upper control limit, your lower control limit, and your center line. Your center line for the R bar chart is R bar, and then you're going to plot your points. So you'll notice that these are not exact. Like I didn't actually write out every single number on the axis here. It's rough, but it gives you an idea of what is happening to the data, because the last part of the question is going to ask you whether or not it's in control. So you need to have a view of the data. So the first data point's down here, second one's a little higher, the third one crosses the center line, the fourth one's up here, the fifth one's down below, the sixth one's right across the center line, and the seventh one is about up there. So I connect these points, and now I can answer the actual question because it says draw the charts, plot the data, and then answer if the process is in control or not. So someone take yourself off mute and tell me, is this process in control? Why or why not?
Yes, because it's within the control limits.
Okay, I've got 1 for yes because it's within the control limits. That would be answered correctly. You would get full points for that. Does anyone want to throw out a different answer? So if someone were to say to me, I don't think the process is in control because even though it's within the control limits, it's all over the place, I would also mark that correct. Because there's a lot of variation. Those ranges from the lowest number to the highest number, even though they're within the limits, they're all over the place. So either answer would be correct and would be marked correctly. So if you just say, yes, all data points are within the control limits, you get all of the points. Perfect answer. But if you look at it and say, well, they're within the limits, but something weird is going on here because it's all over the place, you would also get full credit. And that's also an acceptable answer. If I was looking at the process and someone said to me, well, look, everything's within the limits, I would say, okay, well, tell me what's happening at between these samples, because you've drawn a little, iceberg here that's going to sink the Titanic. I'm down, I'm up, I'm down. What was happening? Why is that happening? Why isn't it closer to the center line? Like, I would ask more questions with this type of variation. So either one of those answers would be correct. All right, people feel good about this? We did a whole lab about this, but it feels like a million years ago. So I just want to make sure everybody's feeling comfortable with it. Yes, I'm going to take your silence as yes. Or you can type in the chat box yes. Okay, we're going for silence is equal to yes. All right. Oh, here we go. Someone's typing in the chat. Thank you. Yes. Thank you, Justin. I appreciate the response. All right. So let's move to the next one. Number 3. This goes back into stuff that we've been talking about. Again, kind of started talking about this before we went on spring break. So before we all left one another. And so you should have some notes. Trent, he speaks for the people? Wow, okay, so Justin, well, then we're done. All right, but we're not actually done. We're only done with that problem. So in this question, we're told that an inspector must inspect a production batch of 15,000 parts using a gauging method. The actual fraction defect rate is 0.02. The inspector's accuracy is given by a P1 of 0.92 and a P2 of 0.8. Determine the number of defects and the expected number of type 1 and type 2 errors. So on your handout that we had from working this chapter, I gave you a table that had all of these formulas written down. We're going to be using those formulas again. This problem might help refresh your memory, but we have done this before. And so the first thing that I want to write is I want to go ahead and write out my given statements because it's been a while. Andrew, I think everybody likes that idea, but I think we can work through it. I think you guys can go. Oh, Trent's giving you a standing ovation for that idea. I think you guys will be able to pull it through. As I said, if you didn't hear me earlier, keep these notes close to you while you do the exam because you will see problems that look basically the same with changed numbers. So essentially, that's what we're already doing, Andrew. So take good notes. The final quantity of products, QF, is equal to that 15,000. That was given information to you. You were also given the defect rate, which is your Q, and that was 0.02. That was given to you in the problem. You're given your P1 of 0.92, and you're given your P2 of 0.8. So we're going to look and say our first answer is the expected number of defects that are being reported. How many defects does this inspector think that they're going to have when you go through all 15,000 parts? Well, that equation is 1 minus P1 minus Q times 1 minus P1 minus P2. Remember your order of operations. In fact, if you have any doubt at all, go ahead and throw an extra set of parentheses around these because the Q is multiplying what's in the parentheses, not just separate from the whole thing. So you've got your 1 minus P1, and then you're going to have your Q times 1 minus P1 minus P2. So keep those separate, otherwise your answer might come out incorrectly. So we've got 1 minus 0.92 minus 0.2 times 1 minus 0.92 minus 0.8. So that whole thing is equal to 1 minus 0.92 minus 0.2 times negative 0.72. That's often going to be a negative number there, that part of the equation. So don't worry about that being negative. It often is. And so this comes down all the way to 0.0944. I'm not done. I need to multiply that by the initial quantity. So I'm going to multiply that 0.0944 times the 15,000 parts. And that gives me 1,416 defects reported. And that is the answer to part A. Part B, we do in 2 sections. So B part 1 is for type 1 error. And type 1 error is equal to 1 minus P1 times 1 minus Q. And so that is equal to 1 minus 0.92 times 1 minus 0.02, or 0.08 times 0.98, which is equal to 0.0784. But I'm not done. I need to multiply that by the number of products, 15,000 times 0.0784, and that gives me 1,176 type 1. That is the answer to part 1 of B. Now, what was type 1 error? Type 1 error is good product that you're going to reject. We call it the producer's risk because it's product that the producer would not sell. They would reject it and not sell it even though it's good. Okay, the second part of part B is equal to type 2 error, and type 2 is a little simpler of an equation. It's 1 minus P2 times Q. And so that's equal to 1 minus 0.8 times 0.02. And that's equal to 0.04004, sorry. And so now again, I need to multiply that by the total number of product, and that is 60. Type 2 is product we say is good and we ship it to the customer, but it's wrong. It's bad. So that's called the consumer risk, is type 2 error, because we let it through our doors even though we shouldn't have, and they got it. So this problem, again, on the exam, you will see one that looks exactly the same except the numbers are different. So you should be able to use the exact same equations and work through the exact same method, just with different numbers. All right, everybody good with that? Okay. So I'm moving on to the next problem. And the next problem has a little more words than I usually like to include, but it's because I'm giving you information for a couple different paths. And we did this one in class as well. It has been a little while. You'll notice that we get defect rates for 3 different parts, part A, part B, and part C. And then we're going to put all of this is together. Andrew, do you need me to go back to anything or you got it? Are you good if I move on? Okay, it's being uploaded. And the papers are as well, so you'll see the full thing if you missed something. The final assembly where you put parts A, B, and C together also have a defect rate given to them. and it says draw the diagram for the process, and then it's asking how many initial parts do you need if the customer order is 25,000, and then how many parts will you have left over for A, B, and C. And this is just really helpful because it's saying if I know what my defect rate is, I know how many I need to start with to make sure I can give my customer what they need. So if your customer orders 100 and your defect rate is 2%, then I know out of those 100, 2 of the units wouldn't be good. So I actually need to increase my start amount so that it compensates for that 2% that are defect. And so that's what we're looking at here. That's what this problem is asking. And so this is actually something that's really, really helpful when you're doing materials planning, is you assume that you're going to have defect rates. And so even with your raw materials, you'll over order a little bit. You don't want to over order a ton because then you're sinking money into raw materials you don't actually need, but you want to go ahead and over order enough that you're going to meet your customer demand. So the customer demand is 25,000. We have all of our defect rates, and we're going to draw a picture first so we see what that looks like, and we're going to calculate what the quantities are. So the first thing I do is I say I have part A, and it goes through its process, and then it's inspected at inspection station 1. And from inspection 1, I get rid of those defects. My defect rate for part A, my Q of A, was equal to 0.05, and that information was given to me. I have part B, it gets processed, it goes to inspection station 2, which gets rid of those defects. And we're going to have a defect rate for part B is equal to 0.02. Andrew's trying to get bonus points in a virtual class. Boy, kind of grubbing for points there, aren't you? Then part C goes to inspection station 3. The defects are removed, and the defect rate for C is equal to 0.07. All of these go to a final assembly, and we're going to call that final assembly. And it has one more inspection, and at this point it's the 4th time we've inspected to get rid of those defects. And that is our Q of the final assembly is equal to 0.15. Your drawing should basically look like this. So I have 3 parts, I have 3 inspection steps, I have a final assembly, I have an inspection. So it's Q sub A for part A, it's Q sub B for part B, Q sub C for part C, because they all have a different rate. So instead of all the processes having the same Q, you were given a different Q for A, B, C, and for final assembly. So I gave them a sub A, sub B, sub C, and FA. Now the goal is that when I get through the inspection, I would have a final quantity, a QF, a big QF, that is equal to 25,000. This is the drawing that represents what's happening. And you do get a lot of credit for doing the drawing right, because I look at the drawing and see that you know what you're wanting to do. Then if you accidentally make a mistake or something when you're doing your calculations, you get partial credit for what you get right. But if I see that you've got the drawing right, then I know you understand what the problem was asking for, and that's important. So the first thing that we're going to look at is we're going to calculate how many materials we needed of each of these parts, A, B, and C, to get that final 25,000. And the way we do that is by calculating each one at a time. So my QA, my quantity, initial starting quantity of A, multiplied by the defect rate, 1 minus the defect rate of A, and multiply that by 1 minus the defect rate from the final assembly. It gives me QA times 0.8075. Now, if I divide 25,000 by 0.8075, I get 30,960. That's how many of part A I need to get 25,000 final assemblies. Now I'm going to do it again for B. For B, it's QB times QB, like football that we're missing, 1 minus 0.02, because that's the defect rate at B, times 1 minus 0.15, because that final assembly defect rate is on all the products, all three of them. And so that means I have Q sub B multiplied by 0.833. And so I'm going to divide 25,000 by 0.833, which is equal to 30,012. Now I'm going to do for C. My QC is going to be 1 minus the defect rate at C multiplied by 1 minus the defect rate in the final assembly, just like all the others. And so that's QC times 0.7905. And so if I divide 25,000 by 0.7905, I get 31,625. Now here's where logic comes in. The largest number is the number that's required. If I have a customer order for 25,000 parts, I have to start with 31,625. So you go with the worst quality rating. That's your constraint. Whatever your weakest link is, that's the strength of your system, right? You're only as strong as your weakest link. That's what's happening here. My worst quality rating is my constraint. So the number of products I have to use to get through my worst quality process, that's the number I'm going to start with for all of my parts. Because I need to make 31,625 final assemblies to get that 25,000 good assemblies to sell. So what do I have left over? I'm going to flip to the back of the paper. My leftover is going to be done by product. So if I need to start, my Q initial, Q0 is what we have for our initial quantity, is 31,625, because that's the worst I had. You guys able to see what I'm writing? Is everybody good? Give me a thumbs up in your window or something. Yes? Okay. So if my leftovers, so my starting quantity was based on C, that 31,625, then to calculate the leftover for my other A and B, I need to subtract what those units are. So the amount that I actually have left over for A is going to be equal to that 31,625 minus 30,960, because that is what I calculated back here as being how many I would need for process A. So 31,625 minus 30,960 means that I have 665 left over of part A. And then I'm going to do it again for part B. And so I have the 31,625 minus 30,012, and that's 1,613 of part B. Obviously, I don't have any left over for part C because I have my C is the constraint. That's that 31,625. So I only have to find for the two parts that aren't the constraint to answer that last part of the question. All right. So that's the complete answer for question 4. All right. Question 5, we're going to be looking at inspection costs. And so we're going to compare two alternatives. Our first alternative is one final inspection at the end. The second alternative is distributed inspection. So I'm just going to divide this in half. My little sheet here. And the first option is going to be final inspection. And this option is going to be option 2, which is distributed, because they have different formulas. So I need to treat them differently. So my given information stays the same, but I have two different cost calculations, so I need the information differently. So here, my stations is equal to 20 no matter what. My cost of processing is equal to $1 no matter what. My batch size is equal to 1,500, and that's the same no matter what. My Q for the entire process for all the stations is equal to 0.03, and that is everyone, both methods are using that same number no matter what. And then I have for my final inspection, my cost of final inspection is equal to $2. This variable there is specific to final inspection only. Okay, I'm not going to need it for my distributed inspection. I'm only going to need that for my final inspection calculation. And so when I'm doing cost for final inspection, I use a formula. C sub B is equal to Q0 times N times the cost of processing plus the cost of final inspection. And so my Q0 is 1,500 there. My N is 20. That's multiplied by 1. And then I add the $2 for final inspection. And so that means it's equal to 1,500 times 22, which is equal to 33,000 even. So my cost of inspection for doing a final inspection only is $33,000. So now I'm going to look at distributed inspection. My distributed inspection has all the same components, except it says in this problem that I'm going to do inspection every 5 steps, and it's 10 cents per step. So my cost of inspection at an individual location is 10 cents per step, and I'm going to do it every 5, which means I've got 5 times 0.1. This is really important. This is the one that you guys are going to have that's a little more complicated. The final inspection is really straightforward. On the question that you have on your exam, I can tell you it's not going to be every 5. It's going to be a different number. So look at your CS, the cost per unit per step, and look at how many steps are taken part before you do a distributed inspection, and you multiply those two together. And so in this example, it's going to be equal to 50 cents. In your example on the exam, it is going to be a different number. So our cost for inspection here, the formula is actually broken out into 5 parts because we're doing inspection every 5 steps. So we still have the initial quantity, and then we're going to multiply that by 5, those first 5 steps, times the cost of processing, plus that cost of inspecting for those first 5 stations. That's the first term. Then we're going to add that to Q dot times 1 minus the defect rate to the 5th, because we're going to go every 5 stations, and we're going to multiply that by 5 times the cost of processing, because we're going every 5 stations, plus that cost of inspection every 5 stations. Add to that the term Q naught times 1 minus Q, that defect rate, to the 10th power times 5 times the cost of processing plus the cost of inspecting every 5 stations. One more term, plus Q naught times 1 minus Q 0 to the 15th power times 5 times the cost of processing plus the cost of inspecting every 5 stations. So what do you have here? You have the initial inspection at those first 5 stations. Then you go 5 more stations in, so you're at 10 stations. Then you go 5 more stations in, you're at 15. And then you go 5 more stations in, you're at 20. So this is the term for the first 5 stations. This is the term for stations 6 through 10. This is the term for stations 11 through 15. And this is the term for stations 16 through 20. This format you're going to have to modify to match however frequently your inspection is taking place. So if it was a total of 21 stations and you were doing it every 7, your exponents would all be 7, 14, 21, not 5, 10, 15. So this is the one that you're going to have to look and say, how often am I doing those inspections, and divide them up evenly by the total number of stations. So crunching the math on this, you end up with 8,250 for the first 5 stations, $7,084.56 for stations 6 through 10, $6,083.75 for stations 11 through 15, and $5,224.32 for stations 16 through 20. And so that grand total is $26,642.63, which is cheaper than $33,000. So our cost of just doing final inspection was $33,000. Our cost of doing distributed inspection was $26,600. So option 2 is cheaper, and that's the one that you want to use. That's your final answer there. Okay, we just have 2 more quick problems. These, thanks for hanging in there. This is probably the most challenging because of this distributed inspection step. So again, as you look over the exam, if you have questions to clarify, please feel free to send those to me. If you want to do a Zoom one-on-one to talk through the setup and make sure you have it set up correctly, I'm not going to set it up for you, but if you have it written out and you want to ask me, is this right? I will confirm whether it's correct or not, and if it's wrong, I'll try to talk you through how to get it to the place where it needs to be. So if you're having issues with this part of the problem, please let me know. This is the one that I think is, you know, I'm not setting out to trick you, but it is complicated. So go slow, and if you have questions, ask. All right, so this was the last chapter we did as part of this book. And so it says that we have a digital scale with a range of 50 pounds. Storage capacity in the digital scale is 12 bits. And we're given what the product specifications are. So we're asking if what's the resolution, and is the resolution appropriate? So measurement resolution is given in our textbook as just being the range divided by 2 to the number of bits minus 1. So this is really straightforward. Range is 50 pounds, 2 to the 12th, because that's the number of bits, minus 1. So that's 50 divided by 4,095, and that's equal to 0.012. So the question is that good enough? Well, the second part, the resolution that you should have, the level of precision you want, follows the rule of 10, and precision is the tolerance divided by 10. So that's equal to 0.01 divided by 10, which is equal to 0.001. Now, 0.001 is less than 0.012, so it is not sufficient. So this is the answer for the resolution question. This is the answer for whether or not it's sufficient. No, it's not, because the resolution desired would be 0.001, and what you have is 0.012. All right, so your last question has to do with how CMM machines would work. And this, again, I told you on the video, if we were at the AAC, we'd actually be using one. But when you're calculating this, it's just equal to the length measured by the CMM is equal to the square root in the difference between the two, the starting point and the end point. So you have A1 minus A2 squared plus B1 minus B2 squared plus C1 minus C2 squared. And so in this case, you have the square root of 75.4 minus 15.07 squared plus 60.2 minus 40.3 squared plus 40.8 minus 20.3 squared. And so that all crunches down to, oh, I guess I didn't do the full math out there. The final answer is 66.753. So you plug that into a calculator and you'll get 66.753, but this is the setup. And so this is the same formula that you'll be using for any of those questions with the CMM. It's just the first coordinate subtracted, or the second coordinate subtracted from the first. So that is it. That is it for the quality module. After that, we're going to go to process planning. Again, for your exam, you get a week and a half to do this, knowing that some of you have other exams that are taking place right now. And so I will post this video to YouTube, and I will also post the pages that I just wrote out so that you have those as well. Does anybody have any questions for me?